Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Let's now talk about cosets and a famous named theorem, Lagrange's theorem. There are a handful of named theorems in elementary group theory that form the cornerstone theorems of the subject. We've already talked about Cayley's theorem. We're going to talk now about Lagrange's theorem. Cauchy's theorem will come later, and the famous Silo theorem, or theorems, will come even later than that in the course. Set products of the form AH, where H is a subgroup of G and A is an element of G, are particularly important, and they have a name. So this set AH is called a left coset of H and G, and the element little a is called a coset representative for the coset. We'll see later that there are other coset representatives. In fact, any element of a coset can be a coset representative. The set of all left cosets of H and G is denoted this way. This is read G mod H, not G divided by H. And so it looks like this. And I will refer to this as the left coset family. That's also a term you may not hear elsewhere, because usually the family of cosets is only of interest when H has another property referred to as normality. Then this becomes a quotient group. So you don't need the term coset family, but we will want to discuss the coset family even if H is not a normal subgroup. So that's why I want the name. The size, or cardinality, of the coset family G mod H is called the index of H in G, and it's typically denoted this way. Some people, I think, use square brackets, but I'm using parentheses, G colon H. So that's the cardinality of G mod H, the coset family. And similarly, the set HA is called a right coset of H in G. A, again, is a coset representative, and the right coset family is denoted this way. I don't know whether there's a language terminology for this or not. So we'll just refer to it as the right coset family. In fact, we're going to deal primarily with left cosets. And so we will refer to a left coset simply as a coset. If we want to talk about right cosets, or if we're talking about both kinds of cosets, we'll use the adjectives left and right in order to avoid any misconceptions. Let's gather together some of the facts about cosets for subgroup H. First, we observe that a subgroup H has the same number of left and right cosets. And this follows from this map F that maps the left coset family to the right coset family, sending AH to HA inverse. You might want to send it to HA, but that's not going to work out. This is a bijection, and so these two are the same cardinality, finite or infinite. Now here are some properties of left cosets, and there are corresponding properties for right cosets, and I'll let you supply the formulation for right cosets and also supply any proofs that are missing, as usual. First, as to equality of cosets. Every element of a coset, AH, is a coset representative for that coset. Because if B is an element of AH, then B has the form A little h for some little h in the subgroup capital H, and so BH is A little h, but little h times h is just h. And so we get AH. And so in fact, BH equals AH if and only if B is in AH, or equivalently, A is in BH. So this is how we check equality of cosets. If we want to know if these two cosets are the same, check one of these two. Next, the same coset of H relation, so that's defined by A is related to B if AH equals BH. This is an equivalence relation on G. And so in view of what we have done up here, A is equivalent to B if and only if B is contained in AH or A is contained in BH. So the equivalence class containing A is precisely the coset AH. That tells us that the distinct cosets of H form a partition of G. All cosets of H have the same size. And this follows from the fact that the multiplication map sending H to AH is a bijection, and so all cosets have the same size as H. This is a coset. This is 1H. Okay, so H itself is a coset. Now we have Lagrange's theorem. Since the distinct cosets in G mod H form a partition of G, and since each coset has size equal to the size of H, and these could be infinite sizes, so I should really probably be saying cardinality. We can deduce that if G is finite, then the size of the order of G is the order of H times the number of cosets, and so the size of G mod H is the size of G divided by the size of H. This is the index of H in G also. It's the size of G divided by the size of H, and here these things have to be finite or this wouldn't even make sense. In particular, then the order of the subgroup divides the order of the group. Go back here again. The order of H divides the order of G because it's equal to the number of left cosets. And that is Lagrange's theorem. So let's state a theorem here to summarize what we've done. Let G be a group and let H be a subgroup. The coset family G mod H is a partition of G into equal-sized cosets. And since one of the cosets is H, we know that they all have size equal to the size of H, with associated equivalence relation here, same coset relation. This equivalence relation is called equivalence modulo H, or mod H. And it's sometimes written this way. A is equivalent to B mod H, means that A and B are cosets, are coset representatives for the same coset. AH equals BH. Lagrange's theorem says that if G is a finite group, then the index of G and H, which is by definition the size of the coset family G mod H, is equal to the size of G divided by the size of H. And so in particular, the order of H divides the order of G. Order and size are the same, as you know, for finite groups. So in words, the order of a subgroup divides the order of the group. For finite groups, obviously. It follows, by the way, then, that the order of an element divides the order of the group, because the order of an element is the same as the order of the cyclic subgroup generated by that element. And Lagrange's theorem says that order divides the order of G. As it happens, the converse of Lagrange's theorem fails. So if the order of G is n, and if K divides n, G does not necessarily have a subgroup of order K. And here's an example. This is a very famous example. The alternating group A4, that is the subgroup of S4 consisting of the even permutations. It has order 12 because S4 has order 24, and we talked about the fact that the alternating group has half the size of the full symmetric group. So it has order 12, but it has no subgroup of order 6. And here is how we can prove that. Suppose that H is a subgroup of A4 and does have order 6. We want a contradiction. Then for any element sigma in A4, not in the subgroup H, we have A4 is the disjoint union of the two cosets. Each of these cosets has size 6, and they are disjoint. So remember, cosets are not subgroups, except for H itself. So these don't have to have the identity in common. In fact, sigma H doesn't contain the identity. So this is a disjoint union of sets of size 6. That's therefore the disjoint union has size 12. That's everything. So that's A4. Now, sigma squared has to be in either H or sigma H. But if sigma squared is in sigma H, then sigma squared is equal to sigma little h for some little h in H. And so sigma equals little h in capital H, and that's false. We picked sigma so that it was not in H. So sigma squared is in H. That shows that the square of every element of A4 lies in H. Sigma was an arbitrary element not in H. Its square is in H. An arbitrary element in H, its square is in H because H is a subgroup. So every element of A4 has the property that its square is in H. That's too many elements, because every 3 cycle is a square of another 3 cycle. And you can check this formula easily. So every 3 cycle must lie in the subgroup H. But there are 8 3 cycles, and I'll let you check that. But H only has size 6. No can do. Contradiction, so A4 has no subgroup of order 6. We can also use this theorem to show that A4 is not isomorphic to the dihedral group D12. That's the dihedral group of symmetries of the hexagon. It has order 12. twice the number of vertices in a hexagon. Specifically, A4 has no subgroup of order 6. We just proved that. But D12 does have a subgroup of order 6, and I'll let you think on that. But the sizes of subgroups is an isomorphism invariant. So we can conclude that A4 and D12 are not isomorphic. That may seem like out of the blue, but this will be important later because eventually we're going to want to determine all groups of order 12 up to isomorphism. In fact, we're going to do that for groups of size, 1 through 15. And we'll talk about that. There's a big business in determining all the groups of relatively small order. And we'll have a discussion about that later. It's quite interesting, actually. It turns out that for the groups of order up to 15, the hardest one is 12. There are 5 groups of order 12 up to isomorphism, and it's a little testy to find all 5 groups and prove that that's it. There are no others. So this is a beginning step in that process. We have 2 of them already, A4, D12. But we also have the cyclic group of order 12, so we actually have 3 of them so far. As mentioned earlier in the book, the Euler phi function, also called the Euler Totient function, is defined as follows. Phi of n is the number of positive integers less than or equal to n that are relatively prime to n. Or put another way, and this is why we introduced the phi function, phi of n is the order of this group Zn star. That's a multiplicative group of integers less than n that are relatively prime to n. Now, some simple group theory that we've already developed using Lagrange's theorem will yield for us a famous old theorem from number theory called Euler's theorem from 1763, and 2 famous corollaries. Fermat's little theorem, 1736, and the Chinese remainder theorem, which has an ancient history dating back maybe to the beginning of the 3rd century AD. So this is, I guess you would say, an application of group theory to number theory. Euler's theorem. Let n be a positive integer. If a is an integer relatively prime to n, then a to the power phi of n, that's the Euler phi function, is congruent to 1 mod n. And this is called Euler's formula. Here's how we would prove it, now that we know some group theory. The order of Zn star is phi of n. If B is in Zn star, then Lagrange's theorem tells us that phi of n is an exponent of B, because the order of B divides the order of the group, phi of n. So phi of n is a multiple of the order of B. That makes it an exponent of B. And since in this group Zn star we are doing things mod n, right, the product mod n, we now can write B to the phi of n is congruent to 1 mod n. Or in other words, B to the phi of n is equal to 1 in the group Zn star. And so if this number is too big to fit, you reduce mod n. That's how you take the product in Zn star. So this is Euler's formula for the elements in Zn star, the integers from 1 to n minus 1. Moreover, any integer a that is relatively prime to n can be written a equals b plus kn, where b is in this group. And so a to the phi of n is b plus kn to the phi of n. And when you multiply this out and reduce mod n, the only term that survives is b to the phi of n, which we have just shown is congruent to 1 mod n. So Euler's formula holds for all integers that are relatively prime to n. Euler's theorem has two interesting and famous corollaries. The first is Fermat's little theorem. If p is a prime and p does not divide a, so p and a are relatively prime, then a to the p minus 1 is congruent to 1 mod p. This is actually just a special case of Euler's theorem. The other corollary is very famous, the Chinese remainder theorem. Let M1 through Mr be pairwise relatively prime positive integers. Then for any integers a1 through ar, these congruences have a common solution. And that solution is unique modulo the product of the m's, m1 through mr. As to proof, if for each I between 1 and r, we can find an integer y sub I that is congruent to 1 mod mi and congruent to 0 mod all the other m's, so mj for j different from I, then we can piece these together, and this linear combination will in fact satisfy all of these congruences. And I'll let you verify that. So, when we look at these congruences, we get a little sneak peek of Euler's formula here. What we need here for yi is some integer to the power phi of m of I, and then that would fit Euler's theorem. So we need an integer z sub I that's relatively prime to mi, and for these we want it to be divisible by mj for j different from I, because then zi to the phi of mi is congruent to 1 mod mi. This is Euler's theorem, because zi is relatively prime to mi, and because mj divides zi, it divides this power of zi as well. So this congruence holds, and we would have what we need to complete the proof. Well, now all we have to do is take zi equal to m divided by mi. That is relatively prime to mi because all the moduli are pairwise relatively prime. And these congruences hold. Mj does divide zi when j is different from I, because mj is still present here in the numerator, and so this power of zi will also be divisible by mj. And that's all there is to it. As to the uniqueness modulo m, which is the product of the moduli, if we have two solutions, w and w prime, solutions to this system of congruences, then their difference, w minus w prime, will satisfy the congruences x congruent to 0 mod mk. For all k, In other words, mk divides this difference, and so m divides the difference. And that tells us that w prime and w are congruent mod m. Hello again, this is Professor Roman. Let's continue the group theory lectures. I want to talk now about the external direct product of groups. This is one important method for constructing new groups from existing groups. And we've discussed direct products very briefly for two groups earlier in the lecture series. I want to extend that now to arbitrary families of groups, finite or infinite. So we'll start with finite families of groups. It extends probably as you would expect. If G1 through Gn are groups, and if the group product in Gk is denoted by an asterisk sub k, we don't want to pin ourselves down here. Some of the groups could be additive, some could be multiplicative, some could be something else, and I'll give you an example in a little while. Then the Cartesian product of these groups is the underlying set for a group under component-wise product. So it looks like this. I'm using juxtaposition for the product in P, but I have to use the specific symbols for the product in each of the coordinate groups. This is called the external direct product of the groups G1 through Gn. The word external is important because there's an internal direct product that we will discuss in due course. They're related, but they are not the same concept. They're isomorphic concepts. We'll talk about that at the appropriate time. If, however, this is the notation. It's the extension of the notation I used before, the X with the box around it, to denote the fact that we're dealing with the Cartesian product that has additional structure, algebraic structure. If all of the groups in the family, all of the groups G sub k, are written additively, if they're all additive groups, if addition is the operation in all of the groups, then I'm going to refer to this group as P as the external direct sum rather than product of these groups, and use this notation with a plus sign with a box around it. I'm going to talk about the unfortunate situation for terminology and notation concerning direct products a bit later, after we've discussed arbitrary families of groups. And you'll see there are some issues that come up here. Non-mathematical issues, just notation and terminology. Here's some examples. The direct sum Z2 and direct sum Z3 consists of these ordered pairs. And this is an example of the algebra there. We've encountered the Klein-4 group, C2 of A direct product with C2 of B. It has these four ordered pairs. But I should mention that the 4 group is often written not in ordered pair notation, not as a direct product, but simply as this set of 4 symbols. And A squared is the identity, B squared is the identity. In other words, A and B have order 2, and the group is defined to be abelian, and so from there you can construct the multiplication table. It's the same group, just looks different. So here's a strange example, not something you probably do, but it makes the point that the operations in each component group can be different. So consider the additive group Q, the multiplicative group Q star, and the group Zn star under multiplication mod n, which I'll denote this way. Then in this direct product, it's called a direct product because not all three of these are additive. We have this group product. So you can see on the right side here, addition in the first coordinate, multiplication in the second coordinate, and addition mod n in the third coordinate. Nothing wrong with this, except it's probably not something that would be terribly useful. But I bring up this example to make the point that it may seem rather inadequate or certainly misleading to use the term product here, direct product for this group, but direct sum doesn't help, and there doesn't seem to be any other reasonable terminology, so we'll go with direct product. Now let's look at arbitrary families of groups. What's interesting here is that generalization of the direct product to arbitrary families of groups, meaning finite or infinite, and with emphasis on infinite, leads to two distinct variations. And in fact, the most useful generalization, the most direct generalization turns out perhaps to be the least useful. So that's just the way it is. You've seen this issue of generalization before. For example, when you generalize the concept of two integers being relatively prime to multiple integers, 10 integers being relatively prime, you also have the notion of pairwise relative primeness as well as just relative primeness, and they're different notions. And arguably, pairwise relative primeness is more useful than relative primeness when you have more than two integers. Okay. We need to recall from Appendix A the notion of the Cartesian product of an arbitrary family of groups. Now, we're thinking now of the groups as just sets, the carrier sets. Cartesian product does not require an algebraic structure, nor does it involve an algebraic structure. This is how we defined the Cartesian product in the appendix. It's the set of all functions. So our family has index set capital I. The Cartesian product is the set of all functions from the index set to the union of the family, with the requirement that f of I belong to g sub I for all little I in the family, in the index set. The individual functions here are, they play the role of ordered tuples of size, whatever the size of I is. So if I is uncountable, all this the ordered tuple idea breaks down. In any case, we call these component functions, and f of I is the ith component of the component function. As also discussed in the appendix, when the family is finite of size n, we generally assume that the index set is the integers from 1 to n, and component functions tend to be identified by their images, which are n-tuples. If you know the domain and you order the domain, then this n-tuple tells you everything you need to know about f. It's equivalent to knowing f. When the family is countably infinite, similarly, we generally take the index set to be the set of positive integers and write our component functions. Again, we write the image, or the sequence of images, sequence of components, if you will, for the component function. It's only when we need to consider arbitrary families that we have to turn to the actual function notation because we don't have these other convenient notations. For reasons that will become clear when we talk about internal direct products later in the book, it's very useful to single out those component functions with the property that all but a finite number of their values or components are equal to the identity. So they're almost always the identity. And to be perfectly formal, here's the definition. F is a family of groups. Here is the Cartesian product. The support of a component function f in the Cartesian product is the set of all coordinate indices, little I, for which the ith component is not the identity. So it looks like this. And a component function is said to have finite support if the support is a finite set, or in other words, if f has only finitely many non-identity components. A couple of examples. This Cartesian product is the product of 4 copies of the integers. So this is a 4-tuple, or in other words, it's a component function. Its support is the set 2, 3 because the second and third positions are the only positions that are not identity values. In this case, we're dealing with additive group here, so 0 is the identity. So this function has finite support, but all the functions, all the component functions here have finite support because the index set is finite. Here's another example. We take the countably infinite family of copies of Q star. Those are the non-zero rational numbers under multiplication. Here is a particular element, a component function, which we've written as a sequence. 1, 2, 1, 4, 1, 6, 1, 8. You probably get the idea, but just in case, a sub k is k when k is even, 1 when k is odd. 1 is the identity because this is a multiplicative group. The support of x is the set of positive even integers, 2, 4, 6, 8. That's where the non-identity elements appear. This sequence, this component function, however, they're all equal, the components are all 1, starting with, what, the 6th, 1, 2, 3, 4, the 6th component on. I think that should be 6th. My arithmetic is a bit weak sometimes. Okay, they're all equal to 1, which is the identity. So the only coordinates that are non-identity are the 3rd and 5th coordinates. So the support is the set 3, 5. This has finite support as well. So now we can define 2 versions of the Cartesian product for an arbitrary family of groups. Again, we don't need any algebraic structure here except for one thing. We need the identity element, which is why we're dealing with groups here and not sets. So let F be a family of groups. The strong Cartesian product, also called the unrestricted Cartesian product of the family, is the set of all component functions. It's the Cartesian product we talked about before for sets. But because groups have an identity element, they have a support. The component functions have a support. That concept is well defined. So the weak Cartesian product or restricted Cartesian product of this family is the set of all component functions that have finite support. So it looks like this. Now the term weak, restricted, strong, unrestricted, they are certainly used in the literature, but not widely used, I think. So it may be necessary for you to explain these terms if you're going to use them in conversation. It's also important to note that the weak Cartesian product makes sense only because groups have an identity element, so that the notion of support is defined. There's no such thing as the weak Cartesian product of arbitrary sets. Now, it's not hard to see that both versions of the Cartesian product of groups are in fact groups under component-wise product. So if you take two component functions in either the strong or the weak Cartesian product, then you can define the product fg of these component functions coordinate-wise, where we're using star sub I for the operation, the binary operation in G sub I. In the case of the weak Cartesian product, of course, you have to verify that the product of two component functions with finite support also has finite support, and I'll leave that for you. The identity function in both cases is the function all of whose components are the identity element, and every component function has an inverse. I've written it in multiplicative notation here, just so you get the idea. So now we can define at last these external direct products. If F is a family of groups, and we use star I for the binary operation in GI, the strong external direct product, or the unrestricted external direct product of the family, and I'll denote it using the symbols I use, but with subscript S for strong, is the strong or unrestricted Cartesian product together with component-wise product. The weak external direct product, or restricted external direct product, and I'll use similar notation but with the subscript W, is the restricted Cartesian product together with this component-wise operation. Now, when the family is finite, these two become the same because the strong and weak Cartesian products are the same. So we get the same underlying set, same product, same group. So we don't need to fuss with the terms restricted and unrestricted. Okay, now we need to discuss the terminology and notation issues. And the problem is there's quite a bit of variation in the literature regarding direct products and also the term direct sum. I searched my library and I poked around a little bit on the internet, and I produced this table here. Some say, and that will include us, unrestricted or strong direct product or sum, restricted or weak, either one of these two, direct product, direct sum. And I'll elaborate on this in a minute. Others use the term direct product for unrestricted case and direct sum for the restricted case. Some use the term Cartesian product for the unrestricted case and direct product for the restricted case. You can see what a mess this is if you look at direct product here and direct product here. They're used in opposite meanings by different authors. So this is a mess. There are, in fact, issues, I think, with all three of the sets of terminology. The use of the terms product and sum can be misleading because some of the groups in the family F may be additive, some may be multiplicative, some may be neither, non-generic specific notations. So to use direct sum or direct product is going to be a little misleading regardless. As to the terminology in column 2, the words product and sum are being used to distinguish between the two types of support. And that seems kind of strange because the terms are unrelated, so I don't care for that terminology, but it is commonplace, so you have to be able to respond to it. As far as column 3 is concerned, I don't like the use of the term Cartesian product for the unrestricted direct product, because Cartesian product does not say there's more than just the set of ordered whatever. It doesn't say there's an algebraic structure. So this is what I'm going to do in terms of terminology. With respect to the terms sum and product, as I said before in the case of finite families, if all groups in the family are additive, I will use the term direct sum and these notations. Otherwise, use the term direct product and these notations. So as long as even a single group is not additive, we will just use the term direct product. Also, since the terms strong and weak admit no ambiguity, those are crystal clear, I'm going to use those terms. So here, in summary, is the whole terminology. Strong external direct sum. All groups additive because of the word sum. Finite or infinite support doesn't matter because of the word strong. Weak external direct sum, all groups additive, but only finite support. And for product, strong external direct product, not all groups additive, finite or infinite support. Weak external direct product, all groups, not all groups additive, finite support. I know this is a lot of terminology. It's sort of unfortunate. You can take comfort, perhaps, in the fact that while this is important stuff, we won't be using external direct products a whole lot in this course. The internal direct products are much more important, although because of the isomorphism between internal and external, and weak external products. Those two concepts are really two sides of the same coin. And I'll say it again. Internal direct products correspond to the weak external direct products, and the same for sums.